Okay, let's try this problem.
Okay.
Okay, all done?
Yep.
All right, plus a constant.
True.
Okay, yep, so we still have to build up that habit. They definitely would take off some credit for that on the test. Okay, because what's the derivative of a constant?
0.
So certainly that's the most general form. It doesn't have to be x plus x squared minus x cubed. It could be x plus x squared minus x cubed plus 6. That would also have the same derivative. Or it could be x plus x squared minus x cubed minus 32. That would also have the same derivative of 1 plus 2x minus 3x squared. Okay, let's see. All right, let's try this problem.
Okay.
Okay, so the first thing that you did is you did some algebra. So that was a good idea because the original expression was something we didn't know how to take the antiderivative of, but we used some good algebra there to simplify that expression. Then I noticed with the new expression, one thing you thought about doing was rewriting the 1 over x as x to the negative 1. And that would normally be a good idea, but as I think we talked about last time, if you tried to apply the power rule to x to the negative 1, you'd end up with something that's undefined. You'd end up trying to divide by 0. So the power rule usually works very well. Looks like you're trying to work it out. So you can write there x to the negative 1. And then how would you apply the power rule for anti-differentiation to that?
+1 is 0. So, yeah, so that wouldn't work. We'd have x is 0 over 0.
And we're not allowed to divide by 0.
Yeah.
Okay. A moment ago when you were thinking about this, it looked like maybe you were applying the power rule for differentiation to it. But if we try to find the antiderivative, we can see that that rule doesn't work for x to the -1. So you remember there's a special antiderivative for that, which is natural log of x. So it's good that you recalled that. We would lose little credit, though, on this problem because remember that the most general antiderivative of 1 over x is the natural log of the absolute value of x. So that's one of those details that we need to keep in mind to get full credit on these problems. Okay. Okay, so that was an issue on that problem. I think the rest of that solution is correct. Okay, I'll go back to my screen. Okay, so let's try this problem.
Okay. So
Okay, so you found C. So first you found the general antiderivative of 1 minus 6x, and then you found the particular antiderivative by solving for the constant. And then you checked your answer. Okay, good. So I think we covered all the bases for that problem. That's good. I'll go back to my screen. Good. All right, here's another problem.
Okay. Okay. Gives the sine of x. So gives us cosine sine. Let's add them with that. So f of x would be equal to derivative of sine of x is cosine of x. So this is negative cosine of x plus derivative of cosine of x is negative sine of x. Derivative of cosine of x. Is equal to derivative of cosine. This is just guess we can check more. So we plug in 0 plus -1 plus 0 plus 4 equals 3. That's good. And then -1 plus 0 plus 5 equals 4. That's good. Okay. Answer.
Okay, let's go back up. Scroll down a bit so I can see the top of the problem. Okay, so you found the general antiderivative of f double prime, and then you found the particular antiderivative by solving for c. And then you did something we were having trouble with last time. You immediately plugged c into the expression for f prime. So that was good. That was something that gave us trouble last time, but here you immediately plugged in c into the expression for f prime. And then when you took the antiderivative of f prime, you used your most complete expression with the 5 in it to get f, so that's good. Then you found a more particular form of f by solving for d, and then you plugged that into d. Okay, so that's a good application of what we were talking about last time. And then you checked everything you could check. So this problem gave us 3 pieces of information, and you were able to check all 3 of those pieces of information. Good. And then you made your check marks to show all of those. Okay, good. So that wasn't a simple problem, but you worked through that. You avoided mistakes. That's good. One thing that you've been doing very well is you've been very careful to avoid mistakes with the pluses and minuses. That's very good because it's easy to make careless mistakes with those pluses and minuses. I don't think we've made a single one of those for a while, so that's good that you're paying close attention to that. That often trips people up. Let's go back to my screen.
Okay.
What's this?
Sine of x.
Good. How do you know?
Because the derivative of cosine of x is a negative sine of x, and so if it's negative cosine of x, the derivative of that is just sine of x.
Okay, good. I just noticed that this was a step that seemed to be giving us a little bit of trouble on the last problem. One thing you can do here to make this more straightforward is you can use the constant multiple rule to take the negative out of the derivative. We can use the constant multiple rule because the negative really stands for -1. So we can take that -1 out. And then what's the derivative of cosine x?
Sine of x.
Take your time on that. My question was, what's the derivative of cosine x?
Negative sine of x.
Good. So as I said, we have to be very careful with the pluses and minuses. So that derivative is negative, and we have the negative in front. So anyway, this is how I would work through this to be confident of my answer. I just wanted to mention this because I noticed that we were having a little trouble with this on that last problem. Well, I think this is the most surefire way to think about that. You can just take the negative sign out of the derivative and take the derivative of cosine x. So the point is, we shouldn't bother taking the derivative of negative cosine x. We should take the derivative of cosine x, and then because of the constant multiple rule, the derivative of negative cosine x is just negative times the derivative of the cosine x. Okay, so you took your time on that, but you did get that correct on that last problem. All right. Okay, we haven't done too many problems with sine and cosine together yet, but you adapted to that on that problem, so that was good. All right, let's try this problem.
Okay.
This is supposed to be a 2. I was hoping we'd be able to see we made a mistake by checking it here, but the problem did not work out the way I was hoping. I should have stopped you sooner. Okay, so your instincts were right. We had made some mistakes on this problem. I let you go on because I thought we were going to be able to catch them, but we should have cut our losses. All right, let me go back to my screen and give you some help with this problem. I'll go back to my screen here. So what's this?
Sine of x. Negative cosine of x.
Okay, yeah, so we are getting a little confused here. Perhaps you're a little tired today, or the ideas might have been getting a little confused in our minds. So this is actually not the derivative of sine of x. The derivative of sine x is cosine x. So what happened here is what I was kind of warning you about in a previous session. You're starting to confuse derivatives with antiderivatives. You're starting to confuse the derivative rules with antiderivative rules. Up till now, we've been doing pretty good with that. Up till now, we hadn't been getting confused about that. In fact, I got confused about it a couple times, but you hadn't been. But today, we're getting confused about that. So the derivative of sine x is just regular cosine x. The reason you thought it was opposite is I think you were getting that confused with an antiderivative rule. All right. So before we can go on, we'll have to get that down because we need these trig functions for the problems we're working on today. So what's this?
Cosine of x.
Okay, good. And what's this?
It's negative sine of x.
And what's this?
Negative cosine of x.
Good. And this?
Sine of x.
Okay. Yeah. So I think we started getting confused between these. I think on that last problem you were taking some derivatives when you should have been taking antiderivatives. I think that's what was messing us up on that last problem. And you ended up taking some derivatives when you meant to take the antiderivatives. Or maybe you were just misremembering which were the derivatives and which were the antiderivatives. I think that's what was happening here. Okay, so why don't we stare at this page for a second and kind of meditate on this for a few seconds and tell me when you feel that you're comfortable with those again.
Yeah, I got it.
Okay, good. I'll stay on my screen for a moment. So what's this?
Antiderivative of cosine of x is sine of x.
And what's this?
Sine of x, negative sine of x. Negative sine of x.
And what's this?
Cosine of x.
And what's this?
Sine of x. Negative cosine of x.
Okay, all right. So we've had these down, but it is easy in the middle of a problem to start getting confused between derivatives and antiderivatives. Well, let's go back to your screen. I think that's what was messing us up on that problem. Let's go back to your screen and take another look. So let's go back to the first point where you were trying to figure out f prime of t.
Right here?
Yeah, and let's check those terms and make sure each of those is correct.
2. This stays the same. And it gives us sine. Should be
Okay, so that one mistake, that's part of what messed us up there. Okay, so that definitely messed us up. I should have stopped you right there. I was thinking that we would be able to check our work at the end and find the mistake, but it got too complicated, so I should have just stopped you right there. So actually, that the rest of that work turned out to be a mistake. We'll have to erase. Let's erase the rest of that work. We should not have gone on and done that. I should have just pointed out the mistake before. Now we'll just have to go back and erase everything past that point and try it again. Okay, and that was the step that had messed us up last time. We put in the incorrect sign there for that. I think maybe we were confusing I think you were maybe taking the derivative of sine rather than the antiderivative. Okay, so let's try again. Good. Good. So it's smarter to start with t equals 0. That's good.
Mm-hmm.
Okay, good. So that's what we talked about, plugging the constant back into the function immediately. Good.
Okay.
Okay, good. All right, so what's our answer?
This line.
Yeah,
right
that's our answer. And I think this would be a little tricky to check because the constant is so complicated. So if you want to, you can try that as homework. You'd either have to just hope for the best and hope that you gotten this right, or you can check this as homework, but we probably spent enough time on that problem already. So we'll stop right there. We did end up with the right answer in any case. So that is the correct answer for that problem. Let me double check. Okay, that's right. Okay, so let's see. So the big thing that was giving us the big thing was giving us trouble there was, I think, kind of maybe forgetting our antiderivatives or mixing up a couple of the mixing up differentiation and antidifferentiation. I know I do that a lot. It's a hard mistake to avoid, but that's the purpose of doing the practice on these. Okay, so anyway, I should have just stopped you as soon as we made that mistake and pointed it out, so that we wouldn't have spent so much time on that. But anyway, we ended up with the correct answer there. Okay, so I'll go back to my screen now. One thing that you did that it was good, you were careful there to try to use t's rather than x's. A couple times you used x's, but I think you caught yourself every time and went back and put in the t's. Mm-hmm. You made a good comment there, which you said that t is kind of an unfortunate variable because it looks like a plus. That's a good point. That's something you have to watch out for. It's important to make sure your symbols are clear. There is a good reason to use t, though, because t stands for time, and time is one of the most important inputs you can have into a function. So it makes good sense that they would give us some functions with t as a variable because time is a very important variable. So there's really a simple solution to our difficulty there, which is write kind of a cursive t. So that would be my suggestion to you whenever you're doing those problems. Just write a cursive t with a little tail on the end. And then I think that should pretty much solve the problem. And that way we won't confuse t with plus. Because you're right, that is something you want to watch out for on those problems. Okay. What's this?
E to the pi, e raised to pi.
Yeah. So what's its derivative?
E raised to pi.
Okay. So you're probably using the exponential rule here, right? But this is not an exponential function. Because an exponential function is a constant raised to a variable. And here we have a constant raised to a constant. And what's the derivative of a constant?
0.
So that was something else that was giving us some trouble on that last problem. The exponential rule only works when the exponent is a variable. It doesn't work when the exponent is a constant. If the exponent's a constant, then the derivative is just 0. What's this?
Zero.
Why?
Because it's a constant.
Yeah, a constant to a constant is constant. Constant just means that it doesn't change. Well, pi never changes and e never changes, so pi to the e is never going to change. So we have to, this is something we talked about in some of the earlier chapters. We have to be careful not to apply the power rule or the exponential rules to constant functions. When something's a constant, its derivative is just 0. All right? Okay, let's try this problem. Looks like you've got some of the sines and cosines memorized.
Yep.
Great.
Okay. Okay.
Okay, that's good that you carefully checked against both of the initial pieces of information. So this problem was relatively straightforward to check. So when you're taking the test, you have to use judgment. There's some problems like the last problem that we were doing where it might be too time consuming to check your work. So you just have to hope for the best and hope that you got it right. But there's other problems like this where it's pretty simple to check your work. So you may as well do that to be confident that you got it correct. Okay, so this gave us a little more chance with those trig functions. So I think we're back on track with the trig functions now. This was tricky. There was lots of pluses and minuses, but we kept our bearings and we got that correct. So that's good. So what's this? Try this problem.
Okay. Let's see.
It's easy to forget, huh? All right, good.
Yep.
So that's good. That's good that you went back and put that in, plus a constant. Okay, good. I'll go back to my screen. Okay, so that problem was a bit of review. Very good. So what did you just apply there? That's what we call the power rule for antiderivatives. The power rule for antiderivatives. Okay, so now let's try this problem. This problem is a little bit different than any of the ones we've done before, but we can adapt stuff we've talked about in order to work this out. So this is another antiderivative we'll need to know for this next section, 5.3. So let's give this a shot.
Okay. Let's see.
Good. Okay, good. So it looks like you worked that out. Excellent. Okay, good. I'll go back to my screen. So one thing that you saw you needed to do is you needed to rewrite this so it's not a fraction. And we can do that using a negative exponent. And something you did that was very good on that step is you labeled this correctly. You saw correctly that this was not f yet. This was still f prime. So that was a good use of labels. And then you were ready to use the power rule for antiderivatives. We increase the exponent by 1, and then we divide by that new exponent. And I think that's the answer that you got. Okay, excellent, good. So that's just an extension of some of the types of problems that we've already been doing. Good. Let's try this one.
Okay.
Okay, and how would you check that answer?
Take the derivative of f.
Yeah, and what would that give you?
It gives you x to the negative fifth.
Okay.
Or 1 over,
Yeah, that's right. Okay, so I'll go back to my screen. So, so that's good. We can do this a little bit mechanically, because the power rule just says raise the exponent by 1, and the coefficient is 1 divided by that exponent. But then you can check to make sure that that's correct. Okay, that was correct. Okay, so that's a new type of antiderivative we hadn't talked about before. And now we know how to do that. Good. Let's try this one. This is, again, a little bit different from the ones before, so we'll have to adapt a little bit to this situation.
Okay.
Okay, let's see. Okay, good. That's good. Let's stay on your screen for a moment. So now, maybe I'll go back to my screen. I'll go back to my screen here. Good. So one thing you could do on this problem to bolster our confidence is we could take a smaller little baby step and say this function is the same as this function. And then we know that we're justified in writing like this. I'm not saying you actually have to write this down, but remember, whenever you're not confident about the algebra, the way to boost our confidence is to take smaller little baby steps. So that's how we would go from here to here. I'm not saying you have to write this down, but we should know in our head that this kind of justifies what we're doing. Okay, so then you got that your answer was this. Let's say that c happens to be 0. Just let's say c is 0, then f of x would be negative x to the negative 3. So use your calculator to calculate this. You can talk me through what you're typing in as you go.
Okay. I'm typing in a negative sign, parentheses 2. Wait, sorry. Parentheses, negative 2, raised to parentheses, negative 3. And again, negative.
So, like this?
Yep.
Okay, that turns out to be incorrect here. We don't, yeah. So we're not actually raising the negative sign to a power here. We're not raising the negative sign to a power. So it should be negative 2
Okay.
to the, and now what?
Negative 3.
Let's see, like this?
Yep.
Okay, I think that'll work. All right, that's right.
For some reason, I get the same answer. I don't know. Weird.
Oh, maybe this wasn't the best example yet. I should have used an example where it makes a difference.
Okay.
Now, what's f of yeah, okay. In this example, it doesn't make a difference. So that wasn't the best example that I gave you here. But this is the safest way to do it. Now, how would we do this? You can talk me through what you would type in here. Or maybe I'll just show you. This is the case where you need parentheses. If you see the difference between these two cases. Because here, we really are raising the negative 2 to a power. Here, we really are raising the negative 2 to a power. Maybe I should have written these out. So this was negative 2 to the negative 3. But this should be negative 2. Here we really are raising the negative 2 to a power. Is that making any sense?
Yeah, I'm just wondering if I've been doing this wrong all along or not. Okay, so would it be wrong to just write in 2 raised to negative 3?
2 to the negative 3.
I guess it depends on your exponent. I don't know.
Yeah, that would be a mistake. So you're saying that you would just cancel the negatives?
Right.
That doesn't work because, again, these parentheses are here to show, you have to take the exponent before you take this negative operator here. So yeah, so no, that wouldn't work in this case. They have to be done separately. Maybe this example is more complicated than it needs to be, though. So let me give you an example that shows this more clearly. This is something we'll need for some of these problems. Okay, so this one is easy. So how would you do this on your calculator?
Negative 2 raised to 4.
Actually, that doesn't work. We have to put that in parentheses. So the point is that when you're, so I should have written it out first. This is something we should write down on paper first before we start trying it. Here, we're raising negative 2 to the 4th power. To tell the calculator that we're doing that, we have to use the parentheses.
Okay.
Let's see. Now how would we do this on the calculator?
Negative parentheses 2 raised to 4.
Okay, in this case you don't need the parentheses, but the main question is, should the negative sign be inside the parentheses?
No.
No. In this case you don't need any parentheses at all, and you could just do it like this. The parentheses wouldn't be wrong in this case. All right, I guess that's pretty tricky. Maybe we'll go on and get to the problems, and then we'll see what specific issues come up that give us trouble with that. So maybe we'll come back to that when we see exactly what we need for those problems. I guess those can be kind of tricky. Okay, let's see.
I think I'll just put everything in parentheses.
Well, the problem is you got to put the parentheses in the correct place, so that won't turn out to be a complete solution. So, for example, in some of these examples, the negative sign goes in parentheses. In other cases, the negative sign doesn't go in the parentheses. So when the negative sign is in the input, it goes in the parentheses. But when the negative sign is in the function, it doesn't go in the parentheses. That's the basic, well, that's the principle right there. When the negative sign is in the input, it has to go in parentheses. But when the negative sign is just in the function, then it does not go inside parentheses on the calculator. All right, well, maybe we'll come back to that. Okay, well, here's another type of problem that's a little bit different from the ones we've done before. Let's see if we can adapt and figure out how to do this problem.
Okay.
Okay, and let's check that.
Okay, so minus 1 is 1/2. 6 over 6. Okay.
Okay, excellent. Good. Okay, good. So you remembered the trick we went over earlier, which is that we can write roots as fractional exponents. So that's good that you remembered that trick. We haven't talked about that for a while. We can write roots as fractional exponents. So you had to rewrite the root as a fractional exponent, so then you could use the power rule for antidifferentiation. And then you got to kind of complicate, when you tried to use the power rule for antidifferentiation, you got a complicated coefficient, 1 over 3 halves. But you correctly simplified that into 2/3. So that was good. Okay, I'll go back to my screen. Let's try this problem.
Right. Okay.
Okay, well that was very good. That was very good. The key thing there is that even though you were having trouble, you just kept thinking about it until you worked it out. So that was good. You had some difficulties, but you kept working at it and thinking about it until you worked it out, and you ended up working out each of the steps correctly. So that was good process. On the other hand, it would be good to go back and really think about this problem and think about each of the steps so that you can go through it with more quickly and with more confidence in the future. So this would be a good one to go back and take another look at. But you did work out everything correctly. So that's good. I'll go back to my screen. So to review what you did on that problem, before you can take the derivative here, you have to rewrite the cube root of x as x to a power. So cube root of x equals x to what power?
1/3.
Now we haven't taken the antiderivative yet. Now we're still not ready to take the antiderivative. Now we need to rewrite this so the x is on the top. Now here's where you got confused at first because you changed the 1/3 back to a 3. But remember, when you move something from the denominator to the numerator, that doesn't have anything to do with fractional or non-fractional exponents. That just means you put in a negative sign. And that's what you figured out. You did some examples and figured that out. So when do you go to fractional exponents? Fractional exponents involves moving between a root and a non-root. So that fractional exponent was involved in the first step. Then the next step was moving the bottom of the fraction up to the top. That has nothing to do with fractional exponents. That is related to changing the sign of the exponent. And you took your time and you worked that out. You eventually got that correct, and you worked out the rest of the problem too. Okay, so that was good that you took your time on that and thought through it. Okay, here's another antiderivative we need to know how to do.
Okay. Plus 1. Okay.
Okay. Yeah, I guess if this was a test question, it would be best to keep those signs in there. Your simplification was right. And you know, we're going to be having to do calculator problems with these. So we are going to have to make some simple simplifications. Otherwise, the calculator is going to be kind of a mess. So the simplification you made was correct. So we should go back and put that in again. If this was the whole problem on the test, you would leave that out to be on the safe side. But I think that's a simplification we'll need as we go on.
Okay.
Okay. Okay, good. Well, we hadn't done a problem quite like this, but you saw that you had to separate the fraction into two separate fractions, and then you worked out the steps of that. Okay, that's good. I'll go back to my screen.
Okay.
So this was your first step. Do you remember, how do you divide two numbers with the same base?
You subtract them. You subtract the exponents.
So what would you get when you do that?
We get 1 over x to, well, sorry. We get x to the negative 3.
Yeah, I don't know. You did it right the first time, so maybe I shouldn't show you this to confuse you. But this would be an alternative approach here. 2 minus 5 is negative 3. And this is actually ultimately what you needed anyway to find the antiderivative. So there's really two different ways that you can do this. If you subtract 5 minus 2, then you have to put the answer that you get in the denominator. But then the next step was just to go back to here anyway. Or if you do 2 minus 5, then you can put that answer right up here in the numerator. All right, well, I don't know. You did it. You did it correctly. The method you used worked, and you got the right answer. So maybe it's best to stick with the method that's working for you there. We may as well just stick with that method that you used since that was working for you. Okay, so all right, that was good. That was the right way to do that problem. Let's try this one. So let's, I think we skipped some steps there, so let's not do that. There's a step between your first and your second steps. So let's write how we could re-express that expression in between your first and your second steps, or in between the question and your first step.
Okay. Oh, yeah, I'll just erase.
Okay, now let's take one more little baby step and write the next expression we can get. Okay, perfect. Good. Well, let's take one more little baby step and write the next expression. If we keep taking baby steps, we're going to run into the next problem, but we'll do it anyway.
Yeah. So
Good.
okay,
What do you have written there in that exponent now?
3/2.
Okay, that's correct. However, if you think back, that wasn't what you had with your first method. What you had before was x to the fourth, if you remember. Okay, so this way is right, and the previous way was wrong. Do you remember what made you think it was x to the fourth? You probably did 2 divided by 1/2.
Right.
But notice, we're not dividing 2 by 1/2, we're dividing x squared by x to the 1/2. And what do you do when you're dividing two numbers with the same base?
Multiply the reciprocal.
The question is, what do you do when you're dividing two numbers with the same base?
You subtract
What do you subtract?
the exponents.
Yeah, you didn't subtract the x's, right? You subtract the exponents. Okay, so you don't divide the exponents, which is what I think you did the first time. You subtract them. Well, again, so this is just a good pointer to, it's always best when our confidence is not perfect to take smaller steps. Because I didn't point out what your mistake was here. I just told you to write out smaller steps, and you did it correctly when you did that way. So on these problems, it's best until we have high confidence that we're not making any mistakes to write out each of the steps like we just did there. Because when people make jumps, they often make mistakes. All right, so this time we're doing that correctly now.
I was just trying to think. I guess maybe I've just gotten lucky in the other problems because I was using the same method.
Let's see, can you see any other problems where you think you might have used that method? That's a good thing to check out.
I can't find any specific.
Well, for example, so the example you have at the top of the page there, 6 minus x squared over x to the fifth.
Right. So,
I don't think you did use the same method because you didn't do 2 divided by 5. You subtracted the exponents. Right? Because you got an exponent of 3 there.
Mm-hmm.
So I think it was just this one problem where maybe I'm confused about how you got the 4. I thought you got the 4 by doing 2 divided by 1/2. Maybe I'm not quite sure how you got that 4. But anyway, the way we have it now is the correct way to do it.
Okay.
Good. Okay, are we done?
I believe so, yeah.
Okay. Yeah, so that's right. That's good that you remember to put the constants back in. Okay, well, you ended up doing that correctly. You were careful at the end of that problem with the fractions, and you simplified those fractions correctly. That looks right to me. Let's see. 3 to the negative 1/2. Okay, yes. So I'll go back to my screen. So how could we rewrite this?
X raised to a minus b.
That's right. When you have two numbers to the same base, you simplify by subtracting the exponents. Okay. And I think that the biggest mistake you made on that last problem is that you didn't actually write out the division. You kind of went straight. From here to here. You didn't actually write out the division on paper. People make far fewer mistakes when they can actually see the problem that they're doing directly on the piece of paper. So when in doubt, it's always better to take smaller steps. That can help us to avoid mistakes. Okay, let's try this problem.
Okay.
Okay. Okay. I think it would be really easy to make mistakes on these problems. but I think you took your time and avoided those mistakes. So that's good. We should put in the constant the first time we take the antiderivative. So the first f of x should have a constant. You're doing that on the earlier problems. Let's see. So 3. Okay, that looks good to me. Very good. I'll go back to my screen. I noticed that when you were doing this division, you rewrote this division as x times x to the negative 1/2. And that's a perfectly good method. So if that's the way you prefer to do that problem, that's fine. I think it's also good to review how we can just do this division directly. How could you divide these directly rather than turning it into a multiplication?
1 minus 1/2.
So what would you end up with?
X raised to 1/2.
Which is what you got with your method as well. If you prefer this approach is okay. This approach is okay too, but it's good to see that we could just do a normal division. How do you divide two numbers with the same base? You subtract the exponents. How do you divide two numbers with the same base? Subtract the exponents. Okay, but this method is also correct. Okay, all right, well, we may have to come back to that later. I think we'll have to do antiderivatives even a little bit more complicated than that, but that's probably enough for those types of antiderivatives right now. Those would be good to go back and practice some more so that you can build up your confidence on those. But now we have another issue. Here's something we haven't talked about for a while. By any chance, do you happen to remember this?
I think it's 1 over x squared plus 1.
Okay, that's a different one of the inverse trig functions. Okay, well, I don't remember these very well. These don't come up that much, so I tend to forget these as well. But this one turns out to be this. I'm cheating by looking at the cheat sheet. All right, because I don't have to take the test. But you will have to have this memorized because you have to take the test. So this is the derivative.
Unfortunately.
Yep. This is the derivative for the inverse sine here. Okay, so here's this one. We haven't really we went over these very early in the course, and then we've done almost nothing with these since then, but now they're back. They're actually going to play actually a more important role in this section than they did before. This one is...
This is just, yeah. This is, I think that's the one I was thinking of.
This is the one you were thinking of. Yeah, the easiest one to remember. Okay, now these are actually, like I say, going to start to play a much more important role in the course than they were before. Okay, so for example, how would you read this equation aloud?
The derivative of the inverse of tangent x equals 1 over 1 plus x squared.
Excellent. Now this is read inverse tangent of x. Inverse tangent of x. But that was good. Excellent. Okay. Now in this chapter though, now we've learned another way to put this into words. What's the other way to put this into words?
Let's see. The antiderivative of 1 over 1 plus x squared is inverse tangent x.
Excellent. Very good. That's exactly right. So now we have to focus on these as antiderivatives. So I think we're gonna have to memorize these. So why don't you stare at this for a while and tell me when you feel you have these memorized.
Okay.
Okay. Well, then try this problem.
That's inverse tangent x, tangent of x. the antiderivative of 1 over 1 plus x squared is inverse tangent x plus c.
Plus c. Okay, very good. That's the way to do it. Yes. Okay, let's try this one.
The antiderivative of 1 over the square root of 1 minus x squared is, let's see, the inverse sine of x plus c.
Okay, yes, that's correct. Good. Okay, good. Okay. By the way, can you see then why all of a sudden inverse trig functions are suddenly useful to us? They're useful because now we can take the antiderivative of much more complicated functions. Without these inverse trig functions, you wouldn't know how to take these antiderivatives. These are not things you know how to take the antiderivative of. You know how to take the antiderivative when there's a lot of stuff in the top of the fraction. But we couldn't have used our earlier techniques to simplify this. You can't simplify this fraction. So the inverse trig functions are useful here because they expand the range of functions that we can take the antiderivative of. Okay. Calculate this.
Okay.
How would you go about doing that?
So the inverse of sine. Oh no, that's derivative. Well, I can use my calculator and type in second sine of 0.3, and I get 0.305.
Okay, good. I just wanted to review to make sure we knew how to do that. So can your calculator calculate inverse sines?
Yep.
Yeah, it's right above the sine key. Sine -1 right above the sine key. So you just use second sine, and then you can calculate inverse sines. For a second there, it looked like you might have been thinking about this in terms of derivatives, but then you saw this is not about derivatives, it's just about finding the inverse sines. That's something else that I think we'll need in this section. Okay, let's see where we're at now. Okay, so I don't have it still anymore, but remember that earlier we had made a table of functions and their particular antiderivatives.
Mm-hmm.
So now we have some new entries to add to that table. Now, we're not going to add this stuff. We're not going to add this to the table because this is just really another type of x to the n, right? We don't need to add this to the table because we're just going to rewrite this as x to the n. And we don't even have to write, say, we don't have to write this either because we convert this into a form of x to the n too. So all that we don't need to put in the table. But what's a new function that we've learned how to take the antiderivative of?
1 over the square root of 1 minus x squared.
That's right, yes.
And that particular antiderivative is inverse sine of x.
Excellent. Okay, so what else could we write over here?
Let's see. -1 over the square root of 1 minus x squared. And that particular antiderivative is inverse cosine of x.
Yeah. Now that I think about it, though, we won't really be needing that.
Okay.
I could have simplified our life here. So what's the other function we can use?
1 over x squared plus 1. And that antiderivative, and the particular antiderivative is inverse tangent of x.
Okay, And I shouldn't have brought up the inverse cosine. It turns out we won't need the inverse cosine. So that reduces our memorization a little bit. You only need to memorize these two. Well, too late. I already had to memorize all three. But you can flush the inverse cosine out of your memory now. We won't actually need that one for this section. These are the only two ones that we'll need. And let's go back and see why. So let's say that we're trying to find the antiderivative of this function. Well, of course, you could do that by using inverse cosine, but we just said that we're actually not going to be using that in this chapter. So what we can do here instead is, do you see we can use our normal constant multiple rule? This is just -1 times 1 over square root of 1 minus x squared. And then the constant multiple rule says that when we take the antiderivative, we just pull the constant multiple out of the antiderivative. And what's the antiderivative of this term?
The inverse sine of x plus c.
Okay. Okay, so this is why you don't actually need inverse cosine in this chapter. I shouldn't have brought that up because your textbook and your instructor are not going to use the inverse cosine in this chapter. They're going to do the problems this way. So we may as well do the problems that way too, so we match up with what the answer keys are going to look like. Okay, so we don't actually need inverse cosine because if you ever saw this particular function, you could just use the constant multiple rule and take the antiderivative of the positive fraction and get it to be inverse sine. Does that make sense?
Yeah.
Okay. So we only need to memorize these two particular antiderivatives, and again, we won't use the inverse cosine in this chapter. We could, but that's not the way your textbook does it, so we won't do it that way. So as usual, it's important to review what we talked about. So it's going to turn out that antiderivatives are absolutely crucial for thinking about integrals. Antiderivatives are crucial for thinking about integrals. That's why we spent so much time on these antiderivatives. So make sure to review how we took the antiderivatives here. Most of these we got right. There was a couple points where we got a little confused about the trig functions. We had to memorize these inverse trig functions. I should have erased this. We didn't. It turned out we didn't need the inverse cosine, so I shouldn't have put that down. We did some brand new types of integrals today that we hadn't talked about before. That would be important to review. That we did. We talked about how to do integrals, or we talked about how to do antiderivatives with negative exponents or with roots. That's going to be very important going forward, so it's important to be comfortable with that. Okay, so there was one more random type of problem that we hadn't gotten to yet. Here's one more type of problem. So this is shifting gears a little. This is a little different from the problems we've done recently. We have done problems similar to this before. Well, we'll give this a shot, see if you can figure out what they're going for here. No. Sorry, excuse me. Sorry, let's do this problem instead. So
okay.
Let's try this.
So we need to find the value of the function at 3. If we want to graph of the function, this is the 0.24. And slope of the function at a certain point. Okay, so the slope at 2,4 will be 10. So okay, so at 2, 4, we have a point. At the slope 10. Slope is 10, so it's very steep. If the slope 10 is rise, 1, so 1. You go over 1, you should go up 15. Something like that. Find f of a given that the graph of f passes 0 to 4. The slope. Okay. Yeah, I'm not sure.
Okay, I'll go back to my screen. When we see a problem that we haven't seen before, the way to work this out is we have to ask, what is this similar to? We have to ask, how is this similar to the questions we've seen before, and try to adapt the methods that we've used for those. Well, what would be a good symbol for what this question is asking us?
The height.
Let's see. Okay, yeah, I can see how I could put it that way. What would be a more concrete symbol? What's the symbol for what this question is asking us? What is the question asking us for?
F of 3.
That's what I was going for.
Okay.
You always need to know what the question's asking us for. Well, that would be easy if they gave you f of x, wouldn't it?
Okay.
Did they tell us f of x?
No.
No. So what did they tell us? Well, they gave us this function here, 4x plus 2. That's a function. Is this f of x?
No.
What is it?
That is slope.
So what can I write here? What function is this telling us?
That's telling us the slope.
Okay. What's the name of that function?
I'm not sure.
Well, one of the main concepts in the course so far has been derivative of a function. What's the graphical interpretation of a derivative? What's the graphical interpretation of a derivative?
The slope of the tangent line to a function.
That's right. So if they tell you the slope of the tangent line, what's another name for that information they're giving you?
The derivative.
That's right. This is a code. This is a code. It means, hey, we're giving you the derivative. But we want to make it more fun than just saying derivative. So instead of saying they're giving the derivative, they're saying we're giving you the slope. But the derivative is the slope. The function that tells you the slope is the derivative. So what
Okay.
would be a good symbol for this function? What's the name of the function for x plus 2?
F prime of x.
That's right. This is asking us for, so this is just a coded way of saying f prime of x is 4x plus 2. Okay, so remember what I was saying was when you see a problem that's unfamiliar, you want to ask, how can I adapt this or interpret it so it looks more similar to the questions that I've seen before? Now, we haven't worked on a problem like this recently, but do you remember earlier when we were preparing for this next test, we did a lot of problems now like this. Do you see how this is similar to the questions we've done before?
Yep.
Okay, so well, let's try to proceed then. Take that onto your screen.
Okay. Okay. So f prime of x equals 4x plus 2. So 1, 2.
You doing that on your screen?
Mm-hmm.
It looks like the screen's kind of frozen up again.
Well, I found the antiderivative.
Hopefully it will unfreeze by the time you get to the answer.
Okay. I found the antiderivative to find the function. And that's 2x squared plus 2x plus c. And now I need to find f of 3. So I can plug 3 into the function. So f of 3 equals 18 plus 6 plus c. So c equals negative 24. I'm not exactly sure how to use the point.
Mm-hmm.
So I give up.
Okay, let's see. Okay, oh, your screen unfroze. Let's go back and look at your screen and see what you've done so far. Okay, so what was this question asking us for?
F of 3.
So I can see why you were trying to work out f of 3 here. However, so point to the equation where it says f of 3 equals 24 plus c.
Right here.
All right, that was legal. That made sense. But your next step is you said c equals negative 24. That doesn't really make any sense. I guess you're just assuming that f of 3 is 0, but there's no real reason to do that. If f of 3 was 0, c would have to be equal to negative 24, but there's no real reason to do that. Okay, well, it's a good thing that we had a chance to go back to do this. This is actually a type of question that we've done together now. We've done this type of problem before, but we might have started forgetting how to do this. All right, well, I think you noticed the information you haven't used yet. You haven't used the point, 2, 4. Well, remember that when we did these problems earlier, what do you need to do in order to solve this? It would really help if you knew c, right?
Mm-hmm.
Well, how do you figure out variables in math? By writing down equations. If you just had another equation, you could use that to find c. If you just had another equation, you could use that to find c. Well, we can use the point to write down another equation. We can use that point to write down another equation. Can you see what I'm saying there? How could we use that point to write down another equation?
I don't know.
Okay. Let's see. So go back to my screen. What would be a good symbol for this number?
X.
Okay, good. And what would be a good symbol for this number?
Y.
Good. Any other symbols we could use for this number?
F of X.
Good. But let's be more specific. What could we put in here to be more specific?
F of 4.
You're saying f of 4 is 4?
I guess.
Let's see.
I'm not sure what other symbol I could use besides Y. I guess is what I mean.
What does it mean? Well, let's... So we don't know exactly what this function looks like. So I'm just going to kind of draw the function. So where would this 2, 4 fit in this graph?
Somewhere at 2, 4. At 2, 4.
So it would be, say, here.
Mm-hmm.
So what's this coordinate?
4.
Good. Let me think how to explain this. So this is the graph of a function. Remember that a function is like a machine that takes inputs and gives you outputs. A function is like a machine that takes in inputs and gives you outputs. Is this number an input or an output?
It's an input.
Good. And is this number an input or an output?
An output.
Right. What do we have to, what would be the input that would give us this output?
2.
Not 4.
Right.
Remember when I asked you earlier what number goes in here, you said 4. But this doesn't mean that f of 4 equals 4. When we say that this is one of the points on the graph, we mean f of the input equals this output. That's what this means. So this is like a code problem. Everything in this problem is in code. This is testing whether we understand some of the ideas that we've dealt with before. This problem is really identical to some of the problems we've done before, but it's in a code, and we have to see what the code is saying in order to work this out. So when we say that this point is on the graph, what we mean is if you plug 2 into the function, you get 4. So for example, is this point on the graph? No.
No.
Why not? Because when you plug 2 into the function, you don't get 5. You get 4. So when they say that this point is on the graph, what that means is that when you use 2 as the input, the output is 4. Does that help? Remember what we're trying to do is write down an equation. We need to write down another equation so that we can solve for C. Can you see how could you make this into an equation? Once you see what I mean, it's pretty simple. The equation is f of 2 equals 4.
Okay.
Now that won't quite help us because we need to solve for C. So here on the left-hand side, we need to write an expression that involves C. Well, do we have any expressions for finding f of 2? How can we figure out f of 2? You can take a look at the work. All the work that we need is what's on my screen now. So let's see. What have we figured out here so far? The problem gave us the slope of the tangent line, 4x plus 2. The problem gave us the slope of the tangent line, 4x plus 2. what's a name for that slope? What function is this?
F prime of x.
And that's what you wrote down here.
Mm-hmm.
Then what did you do next? What did you figure out from f prime?
The function.
Yeah, f. And you got this expression.
Right.
So what's f of 2?
8, 12 plus c.
Right, so we can write that like this. Okay, so remember what we needed was we needed an equation that had c in it, so we could solve for c. And right now the problem is just like the problems that we did earlier, but it's been a while, so you might have forgotten how to do these types of problems. But this is certainly a type of problem that will be on the test. So we needed an equation about c. Do you see how I got this equation?
Mm-hmm.
Okay, so now what?
Solve for c.
Okay.
So c equals 8, 12, negative 8.
Okay, that's right. Now what? Well, remember that earlier we had an expression for f. Here was our expression for f. This was a very nice expression, except that it had an unknown in it. It had this c in it. Now we can write a more accurate expression for f. What can we say f is equal to now?
2x squared plus 2x minus 8.
Right. So do you remember this type of problem from earlier? What you did here is first you found the general antiderivative, 2x squared plus 2x plus c. Then you plugged in the point to figure out what c was. And then you plugged that in to find the more specific antiderivative. If you recall, we did a bunch of problems like this, but it was maybe a week or so ago, and we haven't practiced them for a while. First, we found the general antiderivative. Then we wrote down an equation to find c. And then we were able to get the more specific antiderivative. Now, what was the question asking us for?
F of 3. I'm just kind of confused as to how how do they get 24 plus c?
Let's see, where do I have 24 plus c written somewhere?
I skipped right to 3. Okay. F of x.
So how can we find f of 3?
We plug 3 into the function.
Yeah, which function?
F.
Yeah, which version of the function? Well, this one that we just found.
Mm-hmm. 2 times 3 squared plus 2 times 3 minus 8. So 18 plus 24 minus 8. So 16. F of 3 equals 16.
24. Okay. Okay, so it looks like this wasn't the best problem to do. Instead of doing this problem, we should have just reviewed the more normal problems, because we might have started forgetting how to do those more normal problems. But anyway, we can kind of review what we just did here on this problem, and then we'll be done for today. So one thing is, notice you can't go straight to f of 3 on this. Notice that we weren't really able to find f of 3 directly until the very end of the problem. So we can't, the point is we can't focus too much on the number 3 at the beginning. We can't focus too much on the number 3. So let's review the steps here. The question was asking us for f of 3, but they didn't tell us f. They told us 4x plus 2. What function does 4x plus 2 stand for?
F prime of x.
How do you know? Well, they told you it was the slope. Well, what's the graphical interpretation of the derivative?
The slope.
So when they say it's the slope, they really mean it's the derivative. So we had that this derivative is 4x plus 2. Now the next step you figured out on your own. You figured out that then you could figure out f by using the antiderivative. But then I think you got stuck and you didn't know how to find c. So here was the key. They told us this point 2, 4. How can we when they give you a point on the function, how can we rewrite that as an equation? How can we, when they tell you a point on the function, how can we rewrite that as an equation? What equation is this?
F of 2 equals 4.
Yeah, this just means that the output from the input 2 is 4. So the first thing we could write down is this. F of 2 is 4. And then how did I get this expression here for f of 2? Well, we already knew what f of x was. That was your antiderivative, right? You had a general expression for f of x, so then you just plug that in with the 2 inside of it.
Okay.
And then that gave us an equation that we were able to solve for c, and then we were able to solve the function.